Alrighty, let's begin. So, informally, I've been getting, some questions about, next semester, and and maybe the provost message. I thought it was pretty clear, but yeah, there's like three possible phases where it's, you could say normal, right? Hybrid, right, and online. Right, that's not. So the thing is what I've been saying is you should probably just register and assume that it's probably going to be somewhere between normal and online, although like lectures, right, those will most likely be online, but maybe exams would be face-to-face. We'll still working it out. Now, something that might be, depends about labs, right? If we have face-to-face, right, but we also have social distancing, you might have to have, 10 students per lab, right? So the lab's double, or you could have, like in some labs, you have 1 week LTspice, right? And 1 week fab. I see your question. Just let me finish my thought, or maybe it's you can't hear me. Just design a cure over summer. Yeah. So anyway, now the thing is usually what happens is you do this like week 1, and then you do this week 2, and you could stagger where these people, half the class did LTspice and these waited, right? And then the next week, these people came into fab, and then the next class started the LTspice, or actually, and so that for some people, maybe it would start 1 week later and 1 week later, or earlier, something like that, right? So we're still working it out. But even myself, I found something, the Ad Lamb 2000, which is for about $150. It has a function generator, oscilloscope, and it's all like can be programmed with Python. So I'm working with Applied Devices about that right now, just to see what we can do. So I'm gonna have to have a homework assignment where you guys come up with the best joke over this whole thing. So yeah, they're working on the schedule right now, and we're just trying to come up with things. I know it can seem pretty grim right now, but summer is far away. But the thing is the university has planned out, semesters, like 5 years in advance. So the fact that they're looking into online for the fall, it's actually a good thing, so that we're just not caught short-handed. All right. Anyway, today we're going to talk about system identification. Alrighty. And, before, what have we done? We had an HF, and we've designed a circuit to get a transfer function, right? And we've plotted out the Bode plot, right? and we've used HS, GS, for control systems, right? We've used HS to model spring, mass, and damper circuits, right? So the thing is let's say we've designed our circuit, right? And we have our LTspice plot, or we've made our control system and it should be in control, or we've modeled our spring mass damper, and but that's great, but you have to kind of verify, right? That means test, and that really is like, well, we got to find out what happened. Which, yeah, I would be in my dorm room wondering just what the hell had happened in lab, trying to fit whatever I had into some coherent story, right? So basically, you did do this before the shutdown, where you had an RC circuit, right? And you did a Bode plot. Right. And we didn't necessarily go into too much detail, but yeah, maybe this was supposed to cause a cutoff frequency of 1 kilohertz, and that would have meant an HF of 2 pi 1K S plus, right? That would have been the theoretical thing. However, is that what we got? Right? So how would you go about analyzing it? Well, you could try to find the minus 3 dB point, right? But in a way, it's actually more like the asymptotic plot, where and now we're getting into my hand drawings ability, right? You draw that asymptote, right, of the low frequency. You draw the asymptote of the high frequency. And actually where they intersect would be FC, although in our homework we would have been using omega naught, right? And then how would I tell that it's a first order filter? 20 dB per decade roll off, right? And then here, what would the DC gain be? Well, if I had 0 dB, right, then the gain would be 1. Now, we do spend a lot of time talking about phase, and the thing about the phase is it can be a lot harder to measure the phase, all right? And you might have, and I'm going to draw it over here, is you might have even seen something where it came down, that was 0. It might have went as far as minus 87 and then started creeping up. And there's a few things, is that nothing is ever so simple, right? This resistor has an inductor and a capacitance with it. This capacitor has an inductance, capacitance, and resistor. So this would be the ideal element, the resistor. This would be the ideal element, the capacitor. But these things are all here, and they actually are present. But you're trying to determine what it is, what's the big picture, in this case, a low-pass filter. And so even though the phase might be climbing up, right? Pretty much you can call it a low pass filter. The important thing about the phase is that it's negative, because from a magnitude perspective, minus omega naught S plus omega naught is going to be the same as omega naught S plus omega naught. The difference will show up in the phase. And so with measured data, it tends to be, if you can find out as much as you can from the magnitude, right, information, then use the phase to determine like the sign of things. All right. Some other things just to consider is that, you should by now be able to recognize, that's a low pass. That's a high pass. Band. Notch. Now, yeah, these should all have frequency here, and I'm just ignoring the phase at this point, assuming that we've got a system that's in control. The trouble can arise is that next time we're going to do the step response, right? So the step response of a low pass filter, right, is this asymptotic approach. Step response of this is this exponential to k. This band will kind of look, the shape isn't like that, but it starts at 0, it'll go up, it'll look like exponential decay, but it won't quite go up as far. Then here in the notch, right, you'll get this exponential decay, and then it'll kind of come back up. And this is all in time, and time. And the trouble is sometimes you can confuse this for this, even though it's on different axes. And a thing that we will use is that, response near, or let's just call it time response near start, is seen as all right, in the high frequencies. So let's just take a quick look at we have the step response of a low pass filter, starts off at 0, right? And then it goes up and passes to DC. So around here, these earlier times or small time divisions is showing up here as smaller and smaller or gain, right? And in a similar fashion, the long times, or I should put that here, go to the lower frequencies. So as time progresses, right, you're passing that DC voltage. Well, here the gain is practically 1 as you're passing that voltage, right? And so for a high pass filter, right, at lower times, right, or smaller frequencies, smaller times it's passing that 1, right? And at high frequencies, you're passing a 1, and as time gets big, it's going back down to 0. And so lower frequency, higher frequency, earlier time, later time. So this portion goes there, and this portion kind of goes there. And that can be a way to really remember, so that you can get these questions right on the exam. Also, getting a good night's rest is another study technique I recommend. Okay. So I've recognized that a lot of times these are very hard for me to draw, and so I have these PowerPoint slides, and so I'll be using these today. All right, but any questions so far? Okay. So the title of this presentation is Second Order Filter ID, but we're going to start with a review of the first order. All right. And here we have like the generic transfer functions that you could have for a low pass first order filter, right? Where you have a DC gain term, and then you have your break frequency, right? If you had repeated poles that were the same, you would just have this to whatever order you wanted. And then here you have the denominator of the transfer function in the damping omega naught form. All right. High pass filter, similar. But notice that these denominators for the second order filters are all the same, right? Now these are like what I would call the named filters: low, high, band, notch. There is something called an all pass filter as well, right? But not every transfer function has a name, okay? So if you're given a Bode plot, and I think because I've already drawn on it, it might be easier. To just print out some ones that we haven't seen before. Sorry for doing this now. I thought it would look okay when I did it, but then just while I was doing it for you, it looked a little too busy. LTspice prints everything out in frequency and hertz. So in order to get it to, so in order to have a break frequency at 1 hertz, I have to multiply everything by 2 pi, right? So if that break frequency I know is at 1 hertz, I can go a few orders below. Oops. And a few orders above. Okay. So now when I look at this, I can look at the DC part and see that it's 0 dB, right? All right. So I know part of it. Now, yeah, I could try to find that minus 3 dB point and see, I'm just going back and forth and trying to get it, and I can zoom in. All right. And I'm at about 1 hertz. All right. But if you have clean phase data, right, we know that right at 45, right, that should give me my omega naught at minus 45. Now, again, it can be hard to get clean phase data. But just for looking at it, I go from 0 to minus 90. So that should mean that there's one pole that's active that isn't being canceled by a root. All right. But that's my first indication that it is a first order low pass filter. I mean, the low, then I could come here and try to calculate the slope and see if is it 20 dB, 40 dB, and so on. Right, and so that'll be minus 20 dB per decade slope. All right. But what would that look like if I had some gain? So let's have a gain of 100. And there we go, 40 dB. And just so you notice, right, that let's find the 45. That 45 slope is happening at 36 dB, not minus 3 dB. It's minus 3 dB from whatever the gain is. But notice the phase is still the same. All right. Now, what I was saying is that if the phase isn't exactly synced up, it can still tell you. So if the transfer function is minus that, right? So what I found is that trying to get the minus 45 and the 3 dB point exactly to be at the same point can be kind of hard. However, looking here, I'm going from 180 to 90, right? Now I know that even if this phase is noisy, I know that really I've got an inverted transfer function. All right. And if I wanted, let's say you're making a test question. Hey, what would it be is if we did a 1 kilohertz low pass filter? Well, since I'm doing it, I'm going to start, we'll go 1, at 100K. Oops. All right. Now it might not look like it really shifted much, but notice now before we were going at a much different frequency range. We're going from 0 to minus 90, or 0 to 90, right? Which means it's inverted. If you don't want to invert it, get rid of the minus sign. And you know, I could have an attenuator, right? So here, yeah, the gain is minus 20 dB because I'm multiplying everything by 0.1. So if we take a look at that and then come back to our thing, so that's where the plots are coming from. But really, on an exam, you're not going to have access to that cursor, and when you take real measured data, it's going to be noisy. So it's better to just draw an asymptote from 0 dB out, or for whatever the DC is, and then draw an asymptote of the high frequency response, and then at the intersection, that's your omega naught. And then you can confirm, oh yeah, it's at minus 45. But if it's at, I think 135 from the previous example, you know that it's a minus sign out here. All right. Now, mathematically, if this is the function and this goes to 0, h of s is omega naught divided by omega naught and gain dc. All right. And you can download that file and it'll show you. Now, why does this happen at minus 45 degrees? Well, you take the transfer function and just put in j omega naught and solve, and yeah, you get the 3 dB point, or it's not exactly minus 3 dB, and you get the phase. All right. But yeah, probably a review of your complex numbers is a good idea. So now we have the high pass, right? And yeah, you just need to recognize that it's passing the high frequencies. It's passing the low frequencies. All right. And what you do the same thing. You draw an asymptote, and you draw an asymptote here, and then you can pull out the cutoff frequency here, and then verify that it's minus 45. And then you would fit back to this curve, to this transfer function, right? That's high pass. So omega naught would be whatever 2 pi times 1 kilohertz. And then what is your gain AC? Well, you look here, it's 0 dB, but you don't put in 0. This is the linear term. So how do you convert your dB back into a linear? Right, just take 10 to the gain in dB divided by 20, and in this case that equals 1. So just to, this is basically a worked out example, right? We have a high pass because it starts low and goes high. We have a low pass because it passes low. The phase 0 to minus 90, that means it's first order. Phase 90 to 0, again, strongly, it's a quicker way of finding out what the order is rather than trying to pull the slope off. All right. But I didn't draw the asymptote here. I just pulled it here. So omega naught is 2 pi times 10 kilohertz. And the gain at AC, right? Oh, it's not 0 dB, it's 40. So it's 10 raised to the 40 divided by 20, which is 100. Here, the DC gain is 20 dB. 10, 20 divided by 20 is 10. All right, and it's still the same cutoff frequency. All right. With first order filters, it's really going to look you're really just going to get high and low pass filters. All right. That's not a hard and well, let's just say you can't get a band pass or a notch pass with a first order filter. All right. Now let's move on to second order filters, which can be low, high, band, notch. All right. But any questions so far? All right, so what we've done so far is really the inverse of what we've been doing when we plot a Bode plot. And for most of the exams, or for the exams so far, either it's been a first order high or a low, or it's been a Bode plot of a high or a low, and you could have repeated real roots or different real roots, but we haven't plotted complex roots. All right. Okay. So when I look at this, the gain is higher at low frequencies than at high frequencies, so it's a low pass, right? Before there was one break, now there's two. So this is, in this case, it's easy to see that there's two poles, right? Because you can see these two very distinct breakpoints. And you could pull off a cutoff one point from here and then the other point from here. But as they get closer and closer and turn complex, it can be more difficult. So I'm going to show you more of a generic way to do it. Now, actually, the first way is if you have clean phase data, is that one, you tell it's low pass. The DC gain is easy to tell, right? That's 40. How's that? Is if I set my frequency terms to 0, the omega naughts cancel out. I have gain DC, right? But how to find omega naughts, omega naught, right? Well, it's a second order system. That means instead of going to 0 to minus 90 for a low pass first order system, it goes from 0 to minus 180 for a low pass second order system. And that means your omega naught, which is not the break point. All right. Here, the omega naught is the break point. Here it is, omega naught's the break point. Second order, you can't really say that. Omega naught is just, you could think of it as a geometric mean. And it happens at minus 90. So you take the phase, you come out and find where it's minus 90, and then you drop down, and then you can get your omega naught value, which in this case I'm calling 2 pi times 100. All right. So 2 pi times 100. Well, remember, if these omega naughts are going to cancel out at low frequency, right, they got to be squared, right? So it's 2 pi 100 squared. There's the DC gain term. So we have that. And this is the bit that's right now, omega naught is a bit that's missing. So what we do is we just pull off a gain of the magnitude from j omega naught, right? And why do we do that? Well, here's some, we have to get into our complex math, but we put in S, not just j omega, but j omega naught. And we put that into our transfer function. The numerator is unchanged, but the denominator, right, is S squared becomes minus j squared omega naught squared, which there's our minus sign. Here, it just becomes, sorry, I'm over here. This becomes omega naught. There's an omega naught there, so it becomes omega naught squared, but the j still keeps it imaginary, where here it was j squared, right? And here it was just omega naught. It was the real part. There is no frequency dependence in there. And then you realize the omega naughts all cancel out. You have the DC gain divided by j2 pi, the damping factor, right? So that imaginary part is still there, but all that means is you just pull that into magnitude and phase. That just becomes minus 90, right? And you have the gain DC divided by 2 of the damping factor, right? So that's why it's another reason to see why we extract at minus 90. So if I say, what is the gain at that point, right? All right, here's my 100 hertz is my characteristic frequency. I come up here, get the magnitude, read across, and it's, what is that? It's 1415 dB, right? So this 14 dB is extracted because I've taken where the transfer function is equal to j omega naught. Then I've read it right off from here. And yeah, on exams, there's a range that's acceptable, right? So that's equal to 5. That 5 equals to the DC gain divided by 2 of the damping factor. Since we're just worried about magnitudes, we don't really need this phase information. We solve for the damping factor and we get around 10. And 10 is a lot bigger than 1. And a damping factor of 1 means you're having repeated roots, which means this breaks would get closer and closer to where it happened here, right? And then as it went complex, you'd get some resonance in that curve. Okay. So really, you look at the DC, you pull off from minus 90, right? That gives your omega naught part. Then you get the gain there, which then allows you to solve for the damping factor. So really, the things that it looks complicated, but really you just need to find the gain DC, omega naught, and the damping factor. And so that means we need 3 pieces of information. Now, so remember I said that it's over damped, so you can clearly see these 2 breakpoints, right? But omega naught was 2 pi 100 hertz. Well, omega naught is still 2 pi 100 hertz, but notice there's only 1 break. All right. Doesn't matter, you still follow the same procedure. You bring over at minus 90, you go down and read off the frequency information off of the x-axis and multiply that by 2 pi. So that's the same, right? The gain was the same because it was 40 dB. What's changed is the damping factor, right? So before, right, the gain at omega naught was around 14. Now the gain is around 34. So when we put in that value here and then calculate the damping factor, we're very close to 1. And so this didn't change, that didn't change, this didn't change, but the damping factor changed. And now we'll do our complex roots. Again, 0 to minus 180, you know it's second order, pull it off at minus 90. Still, in this example, I kept everything 100 hertz. So this is the same, these are all the same, but the damping factor is different. I read off the gain at where the transfer function is equal to omega naught. And it's very close to 60 dB. Solve for the damping factor, and it's, you know, around 0.05, which is, you know, very underdamped. So you can see this really very extensive thing. Now, I've showed you where you can pull it off from minus 90. However, hey Ed, what's up?
I'm not sure. So when you substitute the S equals J omega, what happened to the J in the S term? Like, because I can see what happens for the S squared term, but
All right.
J.
You know, maybe let's do it out here now that I'm here. So let's see if oops, options. So let's substitute S equals J omega naught. This term becomes minus omega naught squared because J squared is negative 1. Omega naught times omega naught squared to 2. And the J is there, right? It isn't multiplied by another J. So that's where it went. All right. So if I have gain dc omega naught squared minus omega naught squared plus J to damping coefficient omega naught squared plus omega naught squared minus omega naught, oops, did I just turn it on? Minus omega naught plus omega naught squared cancels. And then we're left with omega naught divided by squared divided by omega naught squared. So they cancel out as well. J2, yep, which then equals, because we really are just going to work with the magnitude, that J becomes minus 90. Okay?
Yeah. So if it's like the, are we just working with the magnitude? Because I thought if we work with the phase, wouldn't I thought the J2Y, you wouldn't use that as like a complex when you use like the complex over real?
I mean, we're using what you might call real numbers because we're dealing with the magnitude over here. And we're choosing to read it at minus 90 degrees. All right. Let me get something. Okay. So, right, I just see that I have, it's a low pass filter. The DC gain I pull off here, right? Gain DC equals 10 to the 0 divided by 20 equals 1. And I see that it's second order, mostly by looking at the phase. All right, but I could measure this slope and find that it's minus 40 dB per decade. All right, I find the minus 90 point. I draw that over and then read off. Now, yeah, I'm drawing it to 1K because I know I know what I generated, right? So that's my 1K spot. All right. So now I know omega naught equals 1K 2 pi to convert it into radians. And now I need H at S equals J omega naught. And I read that. Right? So I need to read that off the chart, if you will. Now this can be really hard, and on exams I try to give you more gradations to see, right? But that looks about minus 6 dB. So this will equal, all right, so I calculate this and divide that into the DC gain. So zeta will equal 1 divided by 2 divided by 10 minus. All right. And I'm hoping that gives me around 1. Okay. Now, that's like the whole process that you would go through for one thing and kind of doing it live. That's pulling it off of minus 90. However, when your phase data is, it's negative, if the phase is going negative, then you know the magnitude of the transfer function in general. But another way to do it, you can do this almost all from magnitude, is that if I just draw sorry, I'm experimenting with using a forget it. So that's one asymptote, the DC part. There's the high frequency asymptote. That intersection should give me 1 kilohertz. All right, now is it, why isn't it here? I could have made a mistake. Most likely, usually it comes out a lot closer than that. But again, on an exam, you're going to be doing this by hand. And so there will be some what you would say slop or oh, I can see. I've drawn it at an angle. I mean, I was kind of drawing it like this. I should have drawn it straight down. Okay. Wiggle room. Yep, that's the the technical term, wiggle room. But what can happen though is in this case, I read off the value from here, right? And it really is about 6, or it's actually the same as the example we had been working on. except instead of 100 hertz, it's a kilohertz, and this is practically 34 hertz, 34 dB, which is minus 6 dB down from 40. Okay, in this example, right, it's minus 6 down from 0. But some people will just kind of memorize that this is always 3 dB, and then it messes up things. So there is some wiggle room that can be had, but when I do an extraction or a problem, I tend to make it pretty obvious. Like, I mean, you can clearly see 2 poles here, and so the damping factor is going to be big. If I had the poles here, it'll be very hard to tell the difference between that and they're exactly on top of each other. All right. And then with a clear resonant peak, you can see that the damping factor should be less than 1. All right. So again, now everything's the same, except I guess, yeah, I changed the frequency to 1 hertz instead of 100. 2 clear breaks, it's overdamped. I have the high frequency gain, this 14 dB, right? I'm pulling this off because I have LTspice. Yeah, I can pull it off from 90 because it's a right? High passes go from 180 to 0. So I'm pulling it off of 90 because it's just easier than doing the other way. But on an exam, you'll probably use the magnitude method, right? Then I can read off whatever the h at j omega naught, which is minus 15. And then you can go through and calculate everything. All right. The difference is that at low, instead of going for a DC gain, we're going for a high frequency gain. And then you get S squared divided by S squared, which is canceled out. I was saying it was 15 dB or 5. Then at HJ omega naught, it's minus 16. Instead of the gain at DC, it's the gain at AC. Yes, there's a minus sign because now that S squared becomes minus omega naught squared. This becomes the same, everything cancels, the phases, and you can see now, yeah, that's where you're reading it off of 90. So the different, you just find that the high frequency gain divided by 2 pi, divided by 2 damping factor. And you can see that the damping factor is 15, right? Which is even bigger than before. The omega naught was 2 pi. And then that's all you really need. Oh, and the AC gain was 5. All right. Now, again, it looks like there's, is that a first order, second order? Because it looks like it's happening. I only see one break. Well, even if there's noise on the phase, you can see that there's more than 90 degrees, way more than 90 degrees phase shift. So it's second order. Then you can confirm that with the magnitude that it's increasing at 40 dB per decade. All right, the gain at high frequencies is 6 dB, right? The gain at j omega naught by reading that is 34.7 millidB. Now, yeah, on an exam, you're not going to be able to read that. It'll probably be 0 dB or something. And then I can see that it's 2 pi times 1 hertz. So I put this into the equation, and the damping factor comes 1, very close to 1, right? Now, here, we see this little peak here, right? It goes up and comes down. That means we definitely have a complex root. Although you can have complex roots in the Bode plot, even if there's no peak here, right? It's still 1 hertz. I can still do this the asymptote method or the plus extracted at 90. But just notice that omega naught is not at that peak. That only happens for damping factors well below 1. Plug that into the equation. The AC gain is very close to 1. The damping factor is 1/2. All right. So high and low pass, fairly easy to do on exams. You just look at the high AC gain or the DC gain, pull off whatever j omega naught is, either through the asymptote method or for the plus or minus 90-degree method. Find the gain at that point and solve for damping factor. Bandpass, it doesn't. What happens is that at h equals j omega, kind of everything cancels out, and there's nothing to really. Or you could say at h equals sj omega, you're getting the midband gain, and there's no frequency information in there. So you kind of either have to pull your point way below omega naught or way above. Now, yeah, you can find omega naught by, in this case, it's at 0 because it's halfway through the change. You can see the derivation in there. But what happens here when S is a lot less than omega naught rather than equal to, right? You get S times 2 times the damping factor times the gain midband, right? In this case, 0 dB divided by omega naught, and then you can solve. Now, in this case, you can either go here or you can go here, but you'll get the same answer. But you can still see, in this case, yeah, there's 2 very distinct breakpoints. But as we get more complex, in this case, the damping factor is slightly less than 1. You're getting one area where it just kind of changes direction all at once, right? And even here, we're kind of getting a resonant peak, right? Okay. And you can, basically in the homework, you use these examples. You just see the shape and then follow the methodology, all right? But to get kind of an idea about what's going on with the damping factor is let's keep the AC gain the same, or DC gain the same, 0 dB. The frequency is the same. It's probably 100 kilohertz, right? When the damping factor is large, you can see these 2 breakpoints. Then as the damping factor gets closer to 1, you can see the breakpoints are merging. And notice the gain at hj omega naught keeps getting higher and higher. And at this blue one, a second order filter can have a minus 3 dB point. In fact, that's a Butterworth filter. All right. So a Butterworth filter has complex poles, but there's no peak. All right. And the transient response, when you see ringing, or if it's any underdamped, you'll see some kind of overshoot with the low pass filter. Right. But notice this cross point, right? It's always the same when the frequency remains the same. Same thing with the high pass. All right. The band pass, a little bit harder to simulate, but you can see as it's, it's less, as the damping factor is reduced, it gets more and more selective. It becomes more and more like an LC resonator. And then here's the notch filter. All right. Now in the homework, yeah, the notch filter is, it's left for you to do. It is difficult. You do have to really go through your complex math because nothing ever cancels out. You end up picking a point and just solving with your complex numbers to find it. All right. So next time, you know what? So everything we learned, it's in the book, but it's not put in a format where here's the Bode plot. Tell me what you've got, right? It really isn't in the book. That's why I have these notes. I have a summation video. I even have an LTspice file, right, that you could eventually download. So here is the low pass filter, right? And all you have to do, so in fact, let's say I was trying to do that notch filter. Actually, a notch filter is just sum of the high and the low, so it's just that node, right? Oops. So here's my notch filter. And I'm trying to match the homework. Another thing you could do is use this to verify what you were getting, right? Oh, I think omega naught's easy to pull off because it's in the center. So you could change this number to whatever you wanted. And then you could look at the gain at DC, the gain at AC, right? And then change the zeta. Okay. And then what it does is it calculates what R and C should be. Because the reason why I don't do is that when you go to do the transient, the behavioral voltage source doesn't work that well. The Laplace, the time domain, and it's better to just do an RLC. But you could backfit the model based on this, right, to check your work. So yeah, not necessarily an exam question. Now, what I've been thinking is the breakout room worked pretty well last time, except I think some people had to go or got bored and didn't realize I came back. But I could do a group exercise where I assign everybody who comes. All right, if there's 40 people, I can have 20 breakout rooms and assign you, and then give you a little problem to work on together. All right. Now, here's a question I think you want to answer is, how do you feel about that? So one person is responding, and so what do we see? I'm open. Okay, Mike. Oh, we got 2 for it, and then a lot of no people not voting. So you know how that works. Okay, we'll see. Oh, it's unanimous. Right. So I know we're running out of time. Where is my... Because, that's the thing is I still have the notes are still there. I have prior videos. But, where are we? So today was what you could call Bode Plot ID. Next time will be transient ID. Then we're going to talk about we have a PWM application. We get more into we have more Fourier applications. Basically, where do these filters come from? And then we actually have modulation, right? And that's homework 14. This is 12. That's 13. That's kind of how to say, this is the project. And then, yeah, they're on the exam. Actually, oops, my bad. That's 11, 12, 13, 14. Okay. So there's a homework for everything. All right. But this is kind of review. This is kind of review. It's actually, everything is review. We're just maybe getting into more detail. This is new, and it's really how radios work. Okay. Whether you're going to like 160 or 132. Okay. Are there any questions before we go? Okay, so I know you're staying safe, so I'll just change it to stay sane. All right, take care.